So we'll see why this happens. So the first question we are going to address is why this minus 2/3 K. Two-thirds of your turbulence kinetic energy. So now this particular part, to understand why this is introduced, we will consider a flow, the same problem that is turbulent plane co-ed flow. Okay. So now consider a channel flow or a plane co-ed flow, let us say plane co-ed flow. So in this, what are the conditions that we have seen? When the flow comes to a fully developed state, we have statistical stationarity and the flow will be homogeneous in two directions. So when a plane turbulent co-ed flow, we get, when it is in fully developed condition, so we do get dou by dou x1 of any statistical quantity is 0, right? And then we also have dou by dou x3 is also 0. That is, we have statistical homogeneity, statistically homogeneous turbulence in x1 and x3 directions in this flow. There are many flows like that where you can get a statistical homogeneity. So now we will see what happens to that if you are going to use this particular condition. Okay. So now when I have shown the data that all the three normal stresses exist in even in this kind of a flow, and then redistribution rate is the cause and all these things we have discussed. But we are now, that is the physics. I have shown you the data from direct numerical simulation where we solved only Navier-Stokes, not RANS equation. So everything is preserved there. So we are not discussing the physics, but our model should also represent the physics, otherwise it will behave very bad, correct? So now we are going to see whether model equation are going to capture this phenomenon. So now if I take the equation, model equation, so in equation set I equal to j equal to 1 in what was the equation number for this Boussinesq? Equation 2, okay. In equation 2, that is your Boussinesq expression. So that means I am taking an expression for one of the normal stress, diagonal term. So I have minus u1 prime. I am trying to see what the Boussinesq is giving for this particular term, right? So now we see I get its nu t of dou ui bar by dou xj, which is dou u1 bar by dou x1, because I and j are set equal to 1 here, plus dou u1 bar by dou x1, and then minus 2/3 k delta 1 right? I is equal to j, delta 1 survives. So now what happens to this dou by dou x1 of a statistical quantity? Statistically homogeneous here, right? So this term goes away due to statistical homogeneity. So if I don't have this minus 2/3 k term, what will happen to your normal stress? It is saying 0. Your Boussinesq cannot set normal stress to 0. That is the primary stress that is being generated, that we have seen from data. So therefore here, without this term, so without this u1 prime will be 0, okay. That is clearly wrong. From data we see that this is positive and it is the largest component in a plane turbulent co-ed flow. Okay, so the models that you make should not be good only for one particular problem. Nobody will use this. Only you will use it. Okay, if you are going to say I have a model and go and use it, it must be working first of all for many types of flows. It must be accurate for many type of flows. It must be numerically stable. That means your code should not crash, and the model must be easy to implement. There are so many considerations must happen. Then only your model will become famous. This is the reason why the Boussinesq is using minus 2/3 k, and therefore now this will be essentially your u1. Therefore u1 prime is now set to 2/3 k. Delta 11 is 1. This is fine. So now at least 2/3 k has been set. But why 2/3 k? Now the other question. Why 2/3 k, or at least we will say why k itself, right? Why 2/3 k and why k? Two questions. Why are we using turbulence kinetic energy? Of course, one argument is this Reynold stresses are turbulent stresses. So obviously, I don't want to use a flow quantity, right? Your mean momentum is a flow quantity. U bar, V bar, W bar, and mean pressure, these are all flow quantities. That is not turbulent at all. Entire turbulence is lumped in Reynold stresses in the RANS equation. So it's always a good idea. It makes sense to model the Reynold stresses based on a turbulent term. So turbulence kinetic energy is on the kinetic energy of the fluctuating motion, and therefore that is one idea. But we will see why it is still being used. I will give you some more arguments here. So now we will add all the three stresses in this particular equation in the Boussinesq. Okay. So what you do now is consider equation 2 and add the three normal stresses from the Boussinesq. So that means we need three expressions here, which is minus u1 prime minus u2 prime minus u3 prime. I am going to add all these three coming from according to the Boussinesq. So we already seen what this will be if I use the Boussinesq. So I will have the first one minus u1 prime is basically 2 nu t here, right? It's 2 nu t dou u1 bar by dou x1. Okay. Now if I take u2 prime over bar, this will be nu t dou u2 bar by dou x2 plus dou u2 bar by dou x2. I am essentially setting I equal to j equal to k to get an equation for minus u2 prime equal to nu t of dou u2 bar by dou x2 plus dou u2 bar by dou x2. So that is here dou u2 bar by dou x2. When I am setting I equal to j equal to 2. Now if I set I equal to j equal to 3, I get 2 nu t dou u3 bar by dou x3. Dou u3 bar by dou x3, and the last term, the sum of three terms. So that is minus 3 2/3 k delta ij. Okay, summing all the three expressions coming from the Boussinesq itself. Now it is ready to see one of the term goes away. Continuity equation, right? So this, due to continuity, it is going away. So that's fine. So I have the sum total of this three Reynolds normal stresses according to the Boussinesq is this. This is equal to now, this is equal to minus 2k, because this also 3 and 3 cancel out. I get minus 2k delta ij, or basically delta ij need not be there because delta 1 1 plus delta 2 2 plus delta 3 3. If I write it, I will get the sum total is here delta 1 1 plus delta 2 2 plus delta 3 3, that is 1 anyway. So I get basically minus 2k here, and this one, what can I write this part as? This I can write it as minus ui prime over bar from your tensor rules, summation of 3 terms. And what is this giving me? K is equal to half ui prime. Is this what we learnt in the theory course, turbulence kinetic energies? So we have, so it is not arbitrary here. There is, if you look closer, it is revealing some nice information, okay, and therefore 2/3 k is used here, okay, and the k being used. So we will see here. So sorry, this is the k here. K is used here because of this particular reason. So we will see why 2/3 k is coming into picture. Is this clear? Okay. So basically in the Boussinesq, minus 2/3 k is introduced. So now we see why turbulence kinetic energy is introduced, right? Because we want a turbulent quantity to represent the Reynold stresses, and we actually recovered the k expression when we add the 3 normal stresses in the Boussinesq. This is what we get. Okay. So now this explaining. This explains why k is used. Okay. So now 2/3 k. Now what we do is to get why 2/3 k. For that we simply look at this expression for turbulence kinetic energy, which is k is nothing but your half of u1 prime average plus u2 prime average plus u3 prime average. Now if I am going to consider a flow where it is statistically isotropic turbulence, so we have discussed what is a statistically homogeneous turbulence, that is in a particular direction the gradient of all the statistical quantities are 0, that we have discussed here. Dou by dou x1 of a mean quantity is 0, statistically homogeneous in that x1 direction. But if I am going to take statistically isotropic turbulence, that means the anisotropic nature is gone. I just need one single stress component to represent the whole flow, okay. Whether that kind of a flow exists or not, we don't worry about it, but that is a simplification we can consider. There can be zones within a generic turbulent flow where there can be statistically isotropic turbulence can exist. Even in a generic flow where there is a lot of anisotropy, there may be some pockets in the system where it can be statistically isotropic. So we consider, okay, here consider statistically isotropic turbulence. You should never drop this statistical term, okay. So many get confused that isotropic turbulence means u prime is equal to v prime equal to w prime. That is not we are talking about. We are looking into the statistical nature of it. So it is when you have this statistical isotropic turbulence, what this means is the 3 RMS are same. So that means it is u1 prime over bar is equal to u2 prime over bar equal to u3 prime over bar. When that occurs, I get k equal to 3/2 u1 prime. When all three are same, I can use only one diagonal component to represent. So this becomes 3 times. So 3/2. So what is this giving me then? What is u1 prime now? Because that is what I want to close in my RANS equation, right? Reynold stresses using Boussinesq. So now I get this as 2/3 K. Now you know why 2/3 K has appeared. Okay. Therefore, 2/3 is used. Okay. Please note all these points in the textbooks. It may not have all this information. Please take notes. Okay. Is this clear? Any other doubts on this? No? So we'll close here today and then we'll continue. Any questions? Welcome. Sorry? Yeah. Okay. This has to be sum total will be 1. That is true. It's wait. If I am going to add these three. Okay. So this is incorrect because this is only minus 2/3 K delta 1 which is 1. So we don't have to. This is mathematically incorrect. That is true. Correct. So this is actually just. So this is actually 1 in each of this. In the next expression, it is minus 2/3 K delta 2. So that is nothing but minus 2/3 K. Delta 2 is anyway 1. That is correct. So this is that you take it out. It is used, yes. Boussinesq is used for closing incompressible turbulence as well as compressible turbulence, yes. So the turbulence models that we discuss in this course is applicable also for compressible turbulent flows. It is straightforward to use the models here for, let's say, weakly compressible flows, that is, let's say, in subsonic conditions, Mach 0.5, 0.6 or so on. But if you have transonic, supersonic, hypersonic flows, then the same models that we discuss will have extra terms. So some correction terms appear, some extra things are required to accommodate those conditions. Because at the end of the day, you need to represent the accurate physics as much as possible through your model. So you will do whatever it takes to capture that. Okay, see you in the next class.